we're going to continue on with chapter 14. I'm going to hang around the capillary a while because the capillaries are so critical to delivering our nutrients and exchanging materials with our tissue. So we really need to understand how a given capillary functions, especially when we go to where we're going next week. The respiratory system and the renal system, if you recall, we named them reconditioning organs. And they recondition because they exchange with the blood. So it's critical that we understand really well how a capillary works. So we can see what's happening at the lungs, and so we can see what's happening at the kidney as well. Okay? And so let's just review the structure of a capillary. What features did we learn yesterday about capillary structure? What did we say? They're porous. Very good. What else?
They're thin.
They're very thin. No smooth musculature. What else is not here? No valves. No outer dense connective tissue. They're very simplistic, right? Which facilitates in their job to do what? What are the capillaries doing? Gas exchange, nutrient exchange. Okay, they're exchanging materials from where to where? Between which two fluids? She said interstitial fluid and the blood plasma. Okay. We learned in order to enhance that exchange, we've got to rely upon our comprehension of active and transport mechanisms. We've got to understand gradients, solubility, all those things. So it's really summarized here in this image. We learned that substances that are lipid soluble to move from plasma to interstitial fluid. Anything fancy going on? Not too fancy, just simple what? Diffusion. It can diffuse through a pore, it can diffuse across a capillary cell, whatever. It's soluble. It's going to diffuse down its gradients. Okay? What about charged particles or larger particles? They may move through by transcytosis if they are probably what type of molecule? Not lipid soluble, like proteins. Okay? Our proteins, and really the large, like big ones, may specifically move by transcytosis. What the heck is that? A form of what? It incorporates exocytosis and also first, what did y'all say? Okay. Endocytosis. Endocytose traffics and then, so it's using vesiculation, right? So we could, if something is like a large protein, we can vesiculate it, move it in a vesicle. What if something's not a big protein, but it's like calcium ion? Can it move from between the plasma and the interstitial fluid? It can through the pores. Okay, it's charged. It's not going to be vesiculated, but it could just do what through the pores? Diffuse through. Okay. Very good. If something's large and not transcytosed, may it be moved across between the two fluids? No. What about our red blood cells? May they be moved between the two fluids? No. Why? Or just too big? I didn't address this yesterday, but what do you think about white blood cells? Can they move between the two locations? What are white blood cells used for? When you hear about them, they're associated with what? Immunity. So with that, do you think white blood cells can move between the two fluids? Yes or no? What do you think? Sure they can. Yes, they can. They're built differently than red blood cells. They're actually very mobile, okay, some of them. And so they can actually get out of the blood and go to the tissue and do their work. So they actually have to get out of the blood to go take care of the rest of the body. Okay, so they certainly can because they're built differently. Okay. They're made to move like that. Very good. So we can see particles moving down their gradient. And we're familiar with chemical gradient. We've become familiar with electrical gradient. But what other gradient what other gradient must we add here? Pressure gradient. Okay, very good. In your picture which you drew yesterday, if we're trying to move substances out, in which way do you think the pressure gradient is driving? The substances? Out. Okay. So on your image which you drew yesterday, draw a large T, just representing pressure, and just draw your little slope gradient. Pressure is greatest in the capillary, and it forces substances out. So the pressure must be what in the interstitial fluid? Lower. And there's still pressure. That's just forcing substances out. For a little familiar gradient, pressure is higher inside the plasma, inside of the capillary, than in the interstitial fluid. And that way substances are pushed down the gradient. Because you read ahead as requested, what is the term for this outward movement of substances from the plasma to the interstitial fluid down a pressure gradient? What's happening here to the blood? What did you? You may have guessed correctly. Filtering. Is that what you said? Filtering. The blood is being filtered. We're forming something called filtrate. Okay? And it's collecting where? In the interstitial fluid. So the term that's happening, we're forcing blood plasma and we're selecting it based on size and permeability. We're filtering the blood. If the pressure gradient is forcing your blood plasma out of the interstitial fluid, the process is called filtration. You cannot see that, can you? I'm going to write this word over here because it's difficult to see. I'm writing. Where there's an outward movement of the plasma into the, which fluid? Interstitial fluid. Could that pressure gradient be reversed? It can. What happens if the pressure gradient's reversed? What is it? Very good. If the pressure gradient is reabsorbed and substances are moving from the interstitial fluid to the plasma, substances are being reabsorbed. Which, if you put it together, it makes sense. If I filtered only, I would run out of what? Nutrients, oxygen. I'd run out of my blood, right? It would all be in my tissues, and I'd be a big fluid-filled jelly bean, right? So after filtration of the plasma to serve the tissues, the blood can reabsorb. Okay. And this is how we pick up, say, nutrients from the digestive system, oxygen from the respiratory system, cortisol from the adrenal cortex. You fill in the blank. Okay. That's how those substances get into the blood. Substances get into the blood by a process called reabsorption, where the pressure gradient switches, but they get out of the blood and dropped off in an area is called filtration. Okay. And what's going to drive this is what? Pressure, and of course concentration gradients as well. If I use the term filtration, are you okay if I use the word filtration? We're going to use it for the rest of the semester, really. And it's dealing with the pressure gradients. We've actually kind of filled in the rest of a bit of our guided notes, but I like to. I think the images help a lot more than sometimes the textual bit. But if you recall, we look at the capillary. We learned that the capillary, remember the blood pressure is declining through the system. The blood pressure in the capillary has declined when compared to, say, an artery or an arterial, but it's still greater than the veins and it's still greater than the venules and veins. But even though it's low, it's still high enough to do what? Still, the pressure inside of the capillary is still great enough to filter. Okay? So don't confuse that all of the pressures declining through the system. It's still enough of a difference between the capillaries and the interstitial fluid to filter substances out, to serve the demands of the tissues. Like we said, distribute nutrients, gases, hormones, fill in the blank, whatever's being dropped off. The pressure is enough to filter it out of the capillary. Figure 14, 18, I really probably should have not shown this. I didn't really go into it much. But as well, other tissues. If you remember, we said our capillaries are arranged in beds. And the capillary beds can not only be controlled by our arterioles, like we've discussed yesterday, but other factors can control. So we can have more precise control over capillary circuitry as well. So I'm gonna skip over that a little bit. But now, after how many weeks? 6 weeks now of physiology, you can probably understand that there's more than one control over whatever we're studying, including capillary circulation. The terms which we've already described include ultrafiltration and reabsorption. We just said filtration, ultrafiltration. It's okay. Either term is okay. We learned that in filtration, there's a net outward movement from the plasma to the interstitial fluid. We also learned that during filtration, large proteins that don't have transcytotic ability stay in the capillary. What else is staying in the capillary? We said also red blood cells. Let's add that on there. And if we reverse the pressure gradients, the capillaries can reabsorb, where interstitial fluid is picked back up into the capillary and then dumped into the general circuit. And this thing is just illustrating, long way around, illustrating that the pressure gradient is reversed. Because if I force fluid out, I now have fluid on the other side, so the pressure gradient has just reversed. Okay with switching sides, basically? That forces reabsorption. Collectively, if I want to talk about ultrafiltration and reabsorption together, we can use that term that we became introduced to yesterday called bulk flow. It's just saying, all together, ultrafiltration, what's filtered out, what's reabsorbed, we can call it bulk flow. The caution I gave you yesterday is a term you can talk about it in the capillaries, you can talk about it in the respiratory system, we talked about it in the river systems, whatever. Okay, it's just looking at the mass comprised movement of something. Here we're looking at plasma and interstitial fluid. And if we look at the capillaries, at the arterial end of the capillary, which process do you think happens more? At the arterial end, there's probably more filtration, and at the venule end, there's probably more reabsorption. Because the pressure continues to do what in the capillaries? Continues to decrease. So we're primarily forcing substances out. As the blood enters the capillaries and as it exits, we tend to reabsorb more. Figure 1417 illustrates this for you. As well, it quantitates it for you, and we're not going to quantitate it as long as you can handle more or less. Okay, the fluid will move down its down its pressure gradient. Excuse me. And so the fluid will always move down its pressure gradient. And this illustration does a really nice job showing you that it's not just only filtration up to here and only reabsorption up till here. It's just a collective process, but when the pressure gradient favors one or the other will happen. But we tend to see more filtration as blood enters the capillary with more reabsorption as it exits the capillary. Any questions about using the term filtration, reabsorption, bulk flow, where this happens, etc.? All right. The capillaries lead into a set of vessels called the venules, and they're just going to collect your capillary fluid. Any transfer of white blood cells, as this abbreviation here, can go right back into the circulatory system. So we have some reabsorption towards these end, and then we're just kind of recollecting capillary blood to lead it into the next vessels called veins. So our venules lead to the veins, and we already talked about the structure of the veins yesterday. We learned that when compared to an artery, there is less musculature, and we said the walls are thinner, so there's less musculature. The connective tissue is not as dense when compared to arteries. But we learned that the lumens are much greater in diameter when controlled to an artery, compared to an artery. So what does that mean? We have lower pressure and lower resistance. The volume is actually going to be greater in the veins, but everything's kind of pooling here. But the larger lumen illustrates that the resistance is less in the vein when compared to an artery. We also concluded yesterday that the blood pressure, although declining, is no longer pulsatile, so it's nice and steady. Where did our pulsatile nature of the blood pressure stop? The arterioles. Okay, stop that pulsing. Very good. This is illustrated if you've ever seen someone with an injury. If you cut a vein, the blood just kind of leaks out. But if you have a really deep damaging injury to a vessel, arterial blood spurts. And I have not had the pleasure of seeing that, so, and I hope that you don't either. I'm sure it's going to be not good. Yeah. So that's another just real example that arterial blood is pulsatile. Okay. And so the next bit of venous structure will be somewhat of a review from our discussion yesterday. We learned that the blood pressure is continuing to decline. We talked about the diameter, the purpose of the diameter of the veins being so large is to drop the resistance, because that blood is no longer pulsatile, pressure's dropping, so we don't want to hinder it any more than already what it's got going on. As well, since we don't have an extra heart down at our toes or wherever, the blood needs help getting through the veins, and so we have these backup mechanisms called valves in the veins as well. So once blood gets to a certain point in a vein, it's not going to go back if everything's healthy in a person. Okay, and we already know that the purpose of a valve is to prevent that blood from going backwards, so it's going to keep moving. In addition to those valves, the veins themselves have difficulty bringing blood back to the heart because we've got gravitational pull, pressure's dropping, right? everything's there to actually keep the blood from going back to your heart. So your body has to have some accommodations to return it. And it has a couple of mechanisms called pumps. And you notice I have the sarcastic air quotes. We don't have any other pumps in our body. We have only one true pump, our heart. But the way in which we're built, some other factors facilitate the return of venous blood. And some of you guys identified this in your lab that you turned in Monday or Tuesday, identifying the respiratory and the muscular pump. Okay. You may recall from our respiratory lab Monday and Tuesday that when we breathe, we actually create a pressure gradient in the thoracic cavity. Okay. That alternates also slightly with the abdominal cavity. So when we increase pressure in the thoracic cavity, pressure in the abdominal cavity probably, what do you think? It alternates. So if I increase pressure in the thoracic cavity, the abdominal cavity pressure will decrease a little bit. And then when I release or decrease the pressure in the thoracic cavity, the abdominal cavity pressure will increase a little bit. When the pressure in the abdominal cavity increases, what does it do to your veins? Your big abdominal vein. High pressure does what to the veins? Kind of, she said constricts it just presses on them, it like squishes them. Okay? And when I push on a vein, blood is going to go out. In which direction? One or two directions? There's one direction because the veins have valves. So it's going to go up. It helps push the blood up. Okay? It doesn't go backwards when you take the next breath because the valves. Okay, so every time you breathe, it helps squish. Okay, so breathing helps return blood. Okay. Also doing what? Helps return blood. The second point. What can help return blood? Just moving. Okay. So if you have poor circulation, you could move. Okay. Or if you're immobile, someone could give you a massage, right, and help return the blood back to the heart. So let's look at the respiratory and the muscular pump. Okay. The respiratory pump is illustrated as you breathe. Okay. For some reason, it's not showing. It says during inhalation, the pressure drops in the thoracic cavity, and therefore we have a reversed, increased pressure in the abdominal cavity. That actually squeezes on the abdominal veins. You see in this image, pressure pushes on that large vein and propels blood up to the vena cava. And we try to return it back to the heart. That pressure creates, as described here, is helps pull that blood back towards the heart. So it's just pushing on the vein, kind of pumping the blood, if you will, back to the heart. And again, it's just a pressure gradient pushing that. So breathing helps return venous blood, as well as physically moving. Okay, so just doing physical activity. If you remember when we talked about muscles in the previous unit, we said skeletal muscles as they contract. We looked at how they squeeze in arterial blood, but it also squeezes on venous blood. And so when we squeeze veins, same thing, because of the valves, the blood will go towards the heart because of the way that the veins are designed. Okay? So just moving is a good way to get blood. So. Okay. What questions do you have about the respiratory or the muscular pump? Or understand? Okay. Figure 1422 further illustrates, just gives an image to show how just physically moving. If you work in a hospital, if you're a nurse's assistant or something like that, you may have put on the boots that give the, what are they? I can't remember what they're called, but does anybody know what I'm talking about? Little pressure boots, and they just kind of squeeze and inflate and deflate, and that's just trying to help encourage circulation through the body, okay, for someone who's immobile or has surgery or injury or something like that. Okay, they're mimicking the muscular pump. Okay. So this image here is to just remind me to review the structure of the vessels between yesterday and today. We talked about the structure of the artery, arterioles, capillaries, venules, and veins. We discussed the pressure as it declines and goes from pulsatile to nice and steady. We also talked about the velocity of the blood flow, how it fluctuates. It's greatest in the aorta, least in the veins, intermediate in the... Did I say pressure or... Yeah, speed of velocity. The pressure drops, the velocity fluctuates. It's intermediate in the... It's actually least in the capillaries, greatest in the arteries, and intermediate in the veins. Sorry about that. What questions do you have about the structure of the vessels, the flow of blood, pressure, etc.? All right, so that brief introduction into capillaries and blood pressure and velocity through the individual vessels. We can also very briefly address the lymphatic system. Has anybody heard of this? You may have heard of, if you've not heard it called the system, maybe heard of your lymph nodes, or you felt them swollen when you're what? When you're sick, okay? And so the lymphatic system is a similar type of vascular, I want to use the term vascular loosely, but it's another set of vessels. And they originate at your capillaries, and they're called initial lymphatics. And it's a backup mechanism to pick up any interstitial fluid that may not have been what? May not have been reabsorbed. Yeah, very good. If we look at the lymphatics, that's one primary role of them. And what happens is, once that interstitial fluid is absorbed into a lymphatic vessel, it's no longer called an interstitial fluid because it's not out in between cells. It's no longer called plasma because it's not in your blood vessels. It's called what? Lymph, because it's in your lymphatic vessels. Okay? And so what happens is it's a way to pick up big proteins that maybe aren't transcytosed. So we can get like insulin or whatever, we can pick them up. Here, because of the way that the lymphatic vessels are, they're built differently than any vessel which we've seen so far. So we can pick up large things, larger sized particles, and larger volumes of liquids, if you will. Should have a similar image of this. Yeah, this is figure 1337 in your textbook. Which color are the lymphatic vessels in this image? The yellow things. Okay. You see how they start here at the capillaries where filtration and reabsorption take place. And so they're to kind of pick up extra stuff, if you will. And it's also a one-way type of transport. They're not going to filter. They're only going to absorb fluid and proteins, etc. Okay. The way that they do this is based on their structure, because structure dictates function. Very good. And the cells of the lymphatic vessels are designed so that they're not adhered together, but they actually overlap one another. And so that they're like one-way little doors. Okay. So when pressure is great around them, the little flaps will open and interstitial fluid will go into the vessel. But when the pressure gradient reverses, the flaps are designed to seal. Okay. So they can let fluid in, and once it enters, it's trapped. Does that make a little bit of sense? So pressure is going to force substances in. You notice it's going to be less size restrictive. Okay, so larger proteins can get in there. We'll see fat globules, all kinds of good stuff can enter into the lymphatic vessels due to their shape. Okay. Eventually, the lymphatic fluid, or your lymph, will be dumped into your venous supply right before it gets to the vena cava. So whatever is in the lymph goes into the general circuit at some point in time. And we look at what the lymphatic system does is one we've already identified, to return any filtered fluid and pick it up. Points 2 and 3. Point 2 you may be most familiar with in its association with the immune system. Okay? Because as lymph travels through the lymphatic system, it goes through checkpoints, if you will, or your nodes. What's in your nodes? Does anybody know what's in your lymph nodes? What's waiting around in there? Some white blood cells, okay, are waiting. Okay? So if any fluid goes through there and it has a pathogen, those white blood cells are right there ready to attack, if you will. Okay? So you can prevent illness, okay? If everything's okay in the body. And that's why when you don't think you're sick and you feel your lymph nodes swelling up, your body's mounting an immune response of taking care of you, if you will. As well, maybe my least favorite part of the lymphatic system is, if you think about your diet, if you take in a diet and there's fats in the diet, fat globules themselves are too big to be reabsorbed in the capillary. Okay, it's just physically no way, okay, which would be good, right? However, big fat globules can enter into the lymphatic vessels. Right? Just dump right in there, and so eventually, well, if you have a high-fat diet, eventually that fat's going to go into where? The veins, the heart, and all your body, right? So it's gonna have an ability to get absorbed from the digestive system. Okay. Figure 1338 illustrates for you the association between the lymphatic vessels and the capillary and the venous supply. You can see kind of checkpoints, if you will, the nodes, and then they're returned into the general circuit. Lymphatic vessels are there as well. What questions do you have about just kind of general introduction into the lymphatic vessels, how they're built, what they do? All right. Well, we'll look at some blood pressure and how it's regulated. We had an introduction into blood pressure. We learned how to measure it. Was it last week? We took our blood pressure measurements. And we're going to look at, well, how does the body control this? I use the word control, so really we know there's two mechanisms. What can control it? Blood pressure. What can control your blood pressure? We know which, in a physiological standpoint, what can control your blood pressure? We said two ways, really. What? Did you whisper?
Sympathetic nervous system.
Okay. So just the autonomic nervous system, or no. Huh? Parasympathetic is the autonomic nervous system. No. Somatics, voluntary muscle control. Autonomic nervous system can control your blood pressure when? Listen to your pass-fail for physiology right here. What can control things all semester, first day, and every day? Nervous system, autonomic nervous system, can control your blood pressure. You got it? I'm going to come back to it. But the autonomic nervous system can control the blood pressure. How? Yes, good. Got a good word. Extrinsically, under what conditions? Time-wise, we said rapidly. Okay? Alternatively, we can control blood pressure endocrine system, which is going to take long-term. Okay, all right. You with me on your pass-fail? Endocrine system, long-term. Nervous system, short-term. We're in the heart. You can't voluntarily control the heart. So autonomic nervous system, which includes sympathetic and parasympathetic. Sympathetic does what to your heart? It increases activity, so blood pressure will probably go up. Parasympathetic nervous system, blood pressure will probably go down. Okay. All right, y'all with me where I started to give the overview? Blood pressure, where we're going in a minute, can be controlled by two things. We're repeating. nervous system under quick, precise monitoring conditions. You can override it to speed it up, slow it down, sympathetic, parasympathetic. Long term, though, we can use the endocrine system and using hormones, which we've actually seen, and I said we're going to get to. Do you remember the hormones we're probably going to talk about? That will change our blood pressure, that influence our blood volume. Who has their handout with them? Handout number, was it 4, the big one? So you got like a star for saying Antidiuretic hormone influences, raises our blood pressure. What else? We're going to see antidiuretic hormone in just a moment, and keep searching. I can never hear you. Not calcitonin. Thank you. You said it. Okay, which one? Aldosterone. Thank you. Remember aldosterone? Look at it in your handout. Aldosterone, what does it do? It has lots of things that it does. Reabsorption of sodium at the kidneys. We said when we reabsorb sodium, we reabsorb water, which brings our blood volume higher, which brings our blood pressure higher. So where we're going to go in just a moment, we're going to summarize what I kind of put you on the spot for. Okay? We're going to summarize how the sympathetic and parasympathetic nervous system can very quickly change your blood pressure. Or if we have prolonging blood pressure problems, the endocrine system can get involved to target which organ? The kidneys. To change our blood volume. And it's going to take a little bit longer than just constriction and dilation of a vessel. So if we look at the blood pressure in our systemic circuit, we know that the blood is going to be distributed through the vessels down a pressure gradient, always moving from the higher to the lower pressure. We also have already summarized this week that our systemic pressure is greatest in the aorta. It declines and is least as it enters the right atrium. We're okay with that pressure gradient. We also know that the greatest change in pressure occurs at which vessels? Arterioles. Because they have high what? What's greatest about them? They have the greatest source of, what's biggest here? What's the greatest thing that's happening here? Greatest source of resistance. Thank you. So they're going to drop that blood pressure. They're going to drop that pulsatile nature. So we're going to see, well, how does our body change our blood pressure to make sure it's in homeostatic set point in that 120/80-ish range under resting conditions. Okay? Well, you now know two ways. We said using the nervous system to quickly change it, or the endocrine system. Okay? One is going to be short term, the other is going to take longer. Okay? So, excuse me. Make reference to summarize that change in pressure. Figure 14.9 illustrates the decline in pressure throughout our vascular system. We can see this is going to have the same kind of chart which we've seen earlier. We're going to start at the aorta, go in the arteries, arterioles, capillaries, venules, and veins. If you look what we're plotting here, pressure through the vessels, and we can see the pressure is described as what? This up and down we said is pulsatile. Okay, it goes from high to low, so it's pulsatile. The blood pressure is definitely pulsatile in our arteries. That's the vessels that we look for when we determine our pulse or our heart rate. Okay? We notice then the blood pressure is still pulsatile as it enters arterioles, but really it should be what by the time it gets into the capillaries? Steady. So if you have a new book, I want you to fix this image. If you have a used book, the previous student should have fixed this. So if you have your book, why don't you turn to figure 14.9, and I want you to flatline the pressure in the capillaries. I want you to get rid of that pulsatile line right there, flatten it out, beginning at the end of the arterioles. So we're just going to try and flatline this. And just do your best. Kind of just flatline that. We don't want pulsatile blood in the capillaries. Everybody see what I did? Yes. Flatline this. Figure 14.9. We're getting rid of the pulsing in the capillaries. And at the end of the arterioles, we're just going to flatten it out. So figure 14.9 further illustrates for us the blood is pulsatile in the arteries as it also enters the arterioles. But due to the high resistance of the arterioles, blood is fluid, steady, if you will, in the capillaries, venules, veins. And we can see this continual decline in pressure. That's throughout the different vessels. Where we're headed now, though, is to look at the general blood pressure in the arteries, systemic arteries that we can measure. Okay, how can that be influenced? And what we summarized is we can control blood pressure extrinsically using the nervous system and the endocrine system. We learned the nervous system is going to give us our quick control. And what the nervous system primarily does is alter peripheral resistance. Okay, that's one thing that it does. I really need to add a second thing on here, so why don't you add a second thing in there? Okay. It does alter peripheral resistance, true, but it also changes the cardiac output. What do you think it does to the cardiac output? Well, depends on the condition. So it'll change it'll say influences peripheral resistance and cardiac output. And that's what we're adding here. Nervous system, one alters peripheral resistance and what? Cardiac output. It doesn't take long, just nervous system can quickly have effects there. If blood pressure conditions prevail out of homeostasis, the endocrine system will become involved. And the endocrine system is going to regulate not resistance and cardiac output, but the volume of the blood. Okay? So endocrine system is going to act on what? X on the what? Which system can change our blood volume? Which organs can change our blood volume? The kidneys. So in this case, our long-term controls regulate blood volume, which is our kidneys do this. So the endocrine system targets the kidneys. Which we'll elaborate in just a moment. So this should be a review from the nervous system and kind of through the rest of the semester. We're maintaining homeostasis. So we're going to need a stimulus, changing blood pressure. We're going to need a receptor. We're going to need I didn't hear what you said. Well, that could, yes. Okay, we're going to need a stimulus. We're going to need a receptor. We're going to need a control center. We're going to need an effector. Okay, so we'll see that similar pathway for maintaining blood pressure as well. The receptors that monitor blood pressure are appropriately called baroreceptors, which makes sense. Baro stands for barometer, measures pressure. Okay, and these receptors monitor pressure. Monitoring pressure. They're called baroreceptors. We have pressure-sensitive receptors in our vessels in which the blood pressure is actually the greatest. And so right in the aorta, okay, and also the carotid sinus. Where's that at? Carotid, where's that? In the neck region, right? So where the pressure can be the greatest is where we have these receptors monitoring the pressure of those areas. Their receptors, afferently, we can generate action potentials to our control center. Our control center should be familiar to us. The medulla oblongata, we've seen it. Throughout the semester, we'll see it again next week as well. And these will have to signal out towards different effector organs. Okay? The heart and our blood vessels are going to be our effector organs in this pathway to regulate blood pressure. We're coming back a little bit. Receptor, control center, effector. Okay. So here we're just doing a quick neural reflex for maintaining blood pressure. Pressure sensors communicate with our control center in the brainstem, which will communicate out to our heart and our blood vessels to precisely keep our pressure in set point range. Obviously, there's two areas or ways in which your blood pressure may be. It may be too high, and it may be too low. So our system is always working to maintain its in the set point. It is summarized for you in the figure on page 7 of your guided notes, as well as figure 1428 illustrates the neural control over regulating blood pressure. It's showing the efferent only. It's not showing the afferent sensors. It would be nice if they actually had afferent nerves shown in here. But we can see the effector organs for controlling blood pressure include this thing is the heart and our blood vessels, arterioles, and some of our veins. If we look at the scenario, right, we've got a little homeostasis seesaw. And if our blood pressure becomes too high, which autonomic nervous system should be turned on and which one should be turned off? If my blood pressure turns up above set point, which autonomic nervous system subdivision should be turned on? Parasympathetic, and I should decline the activity of the sympathetic nervous system. In order to do so, the receptors, the baroreceptors, detect this high pressure, communicate with the medulla oblongata, which will decrease activity of the sympathetic nervous system. Tying into chapter 13, remember from the question, from discussion and also was on the test, Where does the sympathetic nervous system synapse? We said the sympathetic nervous system synapses at the node and also the synaptic nervous system synapses at the node to influence the, what does the node control? Pace. Okay. So the sympathetic nervous system synapses not only at the nodes to control pace, but also at the ventricles, we just said contractile cells to control contractility. Okay. So if we decrease activity at the heart, if we decrease sympathetic activity of the heart, two things happen. Heart rate goes down and contractility goes down. That effectively decreases our heart rate. If our contractility goes down, what else goes down? Cardiac output, but directly, that's actually indirect. The pumping, we set our stroke volume. By contract less often and less forcefully, heart rate goes down, stroke volume goes down. So those together factor out to decrease the cardiac output. On top of that, the parasympathetic nervous system should probably be activated. Okay. And so the parasympathetic nervous system synapses also on the what? What part of the heart does the parasympathetic nervous system act on? We have two options. Not on the contractile cells, so at the nodes. Remember, the vagus nerve synapses at the node to do what to your heart rate? To lower it. The sympathetic activity lessens, stroke volume, cardiac output go down. Parasympathetic activity may increase, so our heart rate continues to decrease a little bit. Is the heart the only effector organ in this pathway? What is the other effector organ? Blood vessels. If my blood pressure is too high, what do you think a lot of my blood vessels are probably going to do? They're going to dilate. They're going to dilate. The resistance will go down, and hopefully my blood pressure will go down back to that point. So in review, if my blood pressure is too high, sympathetic nervous system activity goes what? If my blood pressure is too high, sympathetic nervous system should be turned down. Parasympathetic nervous system should be turned up. Okay. Targeting the heart at the nodes and also contractile cells to decrease contractility, decrease stroke volume, and at the nose to decrease pace. So collectively drops our cardiac output. Good. Also affects at the blood vessels to dilate, which decreases our resistance. In combination, will bring our blood pressure back to that point. So if our blood pressure is too high, stop stimulating, right? The heart and blood vessels. Okay, let's turn down the activity. Conversely, do you think your blood pressure could actually drop below set point? It definitely can, right? So in that case, same type of reflex. What detects the drop in blood pressure? What detects the pressure changes? Baroreceptors, same ones, in the aortic arch and the carotid sinus. They communicate with the medulla oblongata and say, this is too low. I need to fix this by activating which subdivision of the autonomic nervous system? Sympathetic nervous system, and turn down the activity of the parasympathetic. Okay, very good. So if the sympathetic nervous system is activated, we do two things at the heart. increase the pace and stroke volume, which bring our cardiac output up. Also can target our blood vessels to constrict. Constrict to increase resistance, which then brings our pressure back to set point. And it's fast. It's just quick adjustment. It's a neural reflex. Hopefully this is another good example of illustrating the dual innervation of the two subdivisions of the autonomic nervous system, how they counterbalance the keep some factors in set point. Okay, and quick, precise control. What questions at this point do you have about how these two systems, two subdivisions of the autonomic nervous system, can quickly bring our blood pressure back to set point, and how they oppose one another, or the targets which they affect? All right, so that's the quick one, and it took us 10 minutes, so we're going to go into the long term, so that's going to take us a little bit. So we got, remember, our endocrine system is like this, and that, and that, and that goes in the blood, so we're gonna go there. Okay. All right, so in addition to monitoring blood pressure to maintain quickly our neural response to changing blood pressure, we can also utilize chemoreceptors. So it's not just baroreceptors, the other receptors used to monitor our blood pressure. We also have these things called chemoreceptors. So we could see a similar reflex in response to changing chemical levels. The more long-term regulation of blood pressure is going to have to incorporate the kidneys and utilize the endocrine system. Okay, so we're going to see some of our familiar hormones that we became familiar with in the third unit. Okay? The kidneys can be controlled by the endocrine system, and we'll learn next week as well, they can regulate themselves too. So they can be intrinsically and extrinsically controlled by the endocrine system to change our blood volume. There's a direct relationship between volume and pressure. If my blood volume is high, so is my pressure. If my volume is low, my pressure is low. Okay? And so our endocrine system can bring our blood volume up or down if we have a prevailing blood pressure problem that our nervous system can't quickly fix by changing cardiac output or peripheral resistance. So we're going to target the kidney to change blood volume, or we can go through this fun little pathway called the renin-angiotensin mechanism. I'm going to mention it today. I mentioned it 2 weeks ago. We'll further illustrate it next week. So that's what if you remember a couple weeks ago, I said I'll mention it now, I'll mention it in a couple weeks. We won't really fully talk about it, but we'll see how indirect this pathway kind of is. So we're going to change blood volume, and we're going to also activate something called renin-angiotensin mechanism. So picture's worth quite a bit, and so this really summarizes the hormonal cascade that affects the kidney. It looks like a big mess because, as I mentioned, endocrine system does this, then that, and that. And then we can change blood volume, then we can change blood pressure. In this scenario, the body is responding to arterial pressure that's declining. So let's say maybe it's you, and you don't hydrate well, and you drink nothing but coffee, and you exercise in the sun in the middle of the day, right? Your blood pressure is going to go, your blood volume is going to go down, so your blood pressure is going to drop, and your body's got to deal with that, okay? So let's say our blood pressure drops. We've got two really pathways that we can kind of go along. Okay? We're going to look at the direct and the indirect pathway. So let's label this one on the far left. We're going to label this one the direct, and on the far right, the indirect. We'll follow the direct pathway because it's actually going to be more simplistic. Okay? as blood, what we'll learn next week, enters the kidney can actually detect that decline in blood pressure directly. We'll learn that the way that the blood vessels are associated in the kidney, it can determine the amount of blood flow. If the kidney says blood flow's low, the kidney is just going to have less blood flow going through. It's going to make less what? What is the kidney trying to make? Kidneys make urine, thank you. If there's less blood flow, there's less urine. So you're not putting out as much fluid, so you're retaining the fluid. So your blood volume essentially stays up. If I keep my blood volume up a little bit, I should bring my blood pressure up a little bit. Your homework over the night is to review this indirect mechanism. So I want to go over your exams. I almost forgot to give those back for you guys. So your homework is to read chapter 14, this indirect mechanism, this hormonal pathway for maintaining blood pressure, as well as your reading pages for chapter 15. Right? We're out of chapter 14. Your homework overnight is to finish chapter 14 reading and read chapter 15, pages 432 through 445.